Hi guys, welcome back to my channel. In this video, I'm going to show the complete solution to 2021, Time Zone 1, Paper 1. No bullshits, let's go. Question 1, you are given with two lines on the same graph. These two lines, they are almost identical, but shifting higher and lower. The one above is denoted as dot, the one below is denoted as a square. The one above is going to give you a y-intercept of 3. The one below is giving you a y-intercept of 1. And how do we get the absolute uncertainty of the y-intercept, which is done by creating a worst fit line within the error bars. So we can get the least steep one like this one. Make sure it is passing through all the error bars. And the worst fit lines of the steepest one should be like this one. It is still within all the error bar. The absolute uncertainty will therefore be here. As the circle line and the square line, they are completely identical. Therefore, they are giving you the same absolute uncertainty. And how about the fractional uncertainty, which is the delta y over y, as they have the same absolute uncertainty, but a different measured value. The smaller measured value would therefore give you a greater fractional uncertainty, which is the square. The answer is D. Question 2. Now you have a big stone. It is released from rest at a tall building. So initially the stone was stationary, which means on this ball there is only weight acting on it. The acceleration should be same as gravitational field strength, which is 9.81. As it is speeding up, it will be moving down. And as it is traveling down, there will be a drag force going against its motion. Therefore, the acceleration will be smaller than g. The acceleration will be smaller than 9.81. Comparing before and after, the object is definitely speeding up. But the rate is getting weaker and weaker. The answer is D. Question 3. You are given with a position against time graph, and on the graph there is a curved line. You are asked to find the instantaneous speed and the average speed relationship. From time equals to 0 up to 3, the instantaneous speed is always increasing because the gradient of position time graph is the instantaneous speed. And you can find the gradient at A, B, C, and D. They are always changing, always increasing. To compare with the average speed from 0 up to 3 seconds, you should take a look at position A to D, draw a straight line, and this is the average speed. The gradient from A to D directly is very similar to the gradient at position C. So the answer is C. Question 4. There is a car. It took certain time to climb a hill at a constant speed. The mass is 1,200 kg. The rate of GPE transfer is 6 kilowatts. The gravitational acceleration is 10. And the question is the height of the hill. To relate these quantities, we can take a look at power defined as the work done divided by the time taken. Right now, the work done is mgh and then time is t. So the power is 6,000 equals to 1,200 times 10 times unknown height, and it was completed in 20 minutes. But we must convert this one into second. Rearrange it and you will get the height is 600 meters. The answer is C. Next, question 5. We have a mass starting from the top of a ramp, and when it reaches the horizontal part, there is a rough floor, and therefore it will stop eventually. Initially, it was at a very high position, so there was GPE. Later, at the bottom of the ramp, it is moving very fast. Therefore, it possesses certain kinetic energy. In the end, it will be stationary. The energy was dissipated as work done against friction. All these energy, they are identical because of the rule of conservation of energy. Therefore, we have GPE at the top equals to KE at the bottom, and it equals to the work done against the friction. GPE is mgh, KE is half mv squared. Work done against friction is the friction times the distance moved. mgh and the work done against the friction is what we are interested at. The friction can be rewritten as mu mg and then d. The mu, which is known as coefficient of dynamic friction, it is the focus of this question. So let's rearrange it to make it the subjects. It will be mu equals to mgh over mgd. After simplifying, it will be h over d. The answer is D. Question 6. The math is quite tedious, but the physics behind is pretty simple. Let's take a look at the story together. Initially, there are two masses, and they were stationary on a smooth table. And these two give you a very important hint on how to begin with this question. Rest, which means the total momentum being zero. Smooth table, which means there is no net force, and therefore we can use the conservation of momentum. And you can consider this setup as if a cannonball being fired from a cannon. The cannonball is x, the cannon itself, it is y. They were stationary, but after firing, x would be moving to the left, and the cannon itself would recoil to the right, namely Vx and Vy. We are trying to calculate the maximum speed reached by mass y, which means V sub y. Because of the conservation of momentum, let's write the equation as follows. mx ux my uy equals to mx vx plus my vy. U stands for the initial velocity, v stands for the final velocity. On the left hand side, everything is zero because of they were stationary. So mx vx plus my vy makes it 0. And we know their masses as well, which is 3 kg for x and 6 kg for y. Therefore, Vx, it is negative 2 times of Vy. Next clue is the elastic potential energy in the spring being 1 joules. Let's take a look at the top. It is the kinetic energy of x and kinetic energy of y together being 1.0 joules as well, because of the conservation of energy. Elastic potential energy in spring will be the sum of Ke of x and the Ke of y, which is 1.0 joules equals to half mx vx squared plus half my vy squared. And we can substitute all the numbers that you know. 1.0 equals to half times 3 times negative 2vy squared plus half times 6 times vy squared. So we'll have 1 equals to 6vy squared plus 3vy squared. 1 equals to 9vy squared. V subscript y is 1 over 3. The answer is B. Question 7. You are given with an acceleration against displacement graph. Usually, this graph is a crap because we can't study the gradients nor the area in the graph. But with the given information, the mass, you can now rewrite the equation to force being the y-axis by multiplying 40 to each of the y-axis value. The reason is net force equals to m times a, which means the FD graph, it is 800, 400, and 0 here. What is the benefit of having a force against displacement graph, which is the area under graph? Now, the area under graph is representing the work done. Therefore, the answer to this question is the area under graph. You can take it like two separated parts. The left-hand side, which is 400 in height, 2 in width. And then a trapezium is 400 on the left, 800 on the right, and then 2 over here. The total area should be 800 plus 1,200, making it 2,000. The answer is B. Next, question 8. Which of the following is best explained by the molecular kinetic model, which is in a container you can find ideal gas molecules moving around, and we consider these as a tiny particle with no size. And it is A. The equation of state of ideal gas is the PV equals nRT equation. In this equation, you will study the microscopic view of gas particle behavior, the pressure it exerts on the wall, the temperature of the gas, and so on and so forth. We choose A here. The B, C, D options, they're still true if you study them as a big solid, as a big liquid. It's not limited to gases. Question 9, you got two scenarios, one of which is heating up a liquid, the other one is boiling some liquid. For heating up a liquid, we use Q equals to mc delta T. For boiling the liquid, we use Q equals to mL. Q for the heating process is 40,000. The mass is unknown, the C is unknown, but the change in temperature is 20. Q for boiling is 600,000. The mass is unknown and the L is unknown. The question required ratio is the specific latent heat of vaporization to the specific heat capacity of the liquid. So you can make the equation like 600,000 divided by 40,000 equals to mL divided by mc times 20. After simplifying, you will get L over C equals to 300. The answer is D. Question 10, you are given with two ideal gases. They are at the same temperature. Then we are going to compare their average kinetic energy and the average speed. The average kinetic energy of ideal gas molecule is 3 over 2 kBT, and it's also the general rule of kinetic energy, half mv squared. As they have the same temperature, they must have the same average Ke of molecules. So the answer could be B or C. Next one is the speed. The sample with greater mass should give you a smaller speed according to m times v squared on the right. Therefore, the heavier particle X should be moving slowly. The answer is B. Next, question 11. Now you are given with the velocity against time graph, and you have to deduce its displacement against time graph and the acceleration against time graph. Note that it is a simple harmonic motion. Therefore, the A proportional to negative x must be obeyed. When there is a positive A, it implies there is a negative x. Also, the other way around, if there is a negative A, implies there is a positive x. They are always opposite in direction. Therefore, option B is wrong because at this part you can see a positive x. At the same moment, there is a positive a. B is wrong. So as C. Here you can see a negative x. At the same moment, there is a negative a. They are in the same direction. A and D, they are both fine about positive and negative direction. So the next question is, let's use the given velocity against time graph to deduce the corresponding acceleration time graph. The gradient of velocity time graph is the acceleration. It began with a zero gradient line, therefore the acceleration should start at 0. Therefore, the answer is A, because at the starting point, its acceleration was 0. Question 12. Now you're given with a sound wave. Therefore, it must be a longitudinal wave. All sound waves, no matter is it underwater or in the air, they are longitudinal wave. Next, you're given with its frequency, the wavelength, and you are going to travel by a certain time. Then you look for the distance traveled. Speed of a wave is the product of frequency and its lambda, its wavelength. Therefore, the speed of it should be 1000 times 0.33. It is roughly 330 meters per second. After deducing its speed, you can calculate the distance traveled divided by the time taken. So it's 330 equals to the unknown distance divided by 0.002 second. The distance traveled by it should be 0.66. The answer is C. Next, question 13. Double slit interference. You have a monochromatic light of wavelength lambda falling onto a double slit. The slit separation is A. And the lights, they are falling onto a screen which is at Y away from the double slits. On the screen, there are bright fringes. The bright fringes, they are separated in a distance of 55 millimeters. For double slit interference, we should check the data booklet. Equation S equals to lambda big D over small d. S is the fringe separation, so in this case, it is 55 millimeters. Lambda is the given wavelength. D is the slit to screen distance, therefore Y in this case. Small d is the slit separation, therefore it's A in this case. And the question suggests that now lambda, Y, and A, they are all doubled. Now the fringe separation should be doubled as well. So the new fringe separation will be 110. Question 14. Now you're given with a long metal rod, but only half of the rod is effective because it is clamped at the midpoint. So the effective length is 22.5 centimeters. Within this length, there is a first harmonic being created. So the wave is going in this pattern, first harmonic. By this pattern, you can tell the wavelength is 4 times of its length. Therefore, the wavelength in the rod is 90 centimeters. But this is the wavelength inside the rod. The wavelength in air, however, is different. Let's take a look at the V equals to F lambda. No matter is it inside the air or in the rod, they are the same frequency. It is constant. In order to adapt a new medium from rod to air, the wavelength must be changed. The speed is proportional to its wavelength. From rod to air, the speed is reduced by 5 times. Therefore, the wavelength should reduce by 5 times as well. The answer is 90 divided by 5, which is 18. The answer is C. Question 15. You are given with 2 charges, and you are going to deduce the force and the electric field strength relationship. Let's start with the equation of electric field strength defined as force per unit charge acting on a positive small test charge. The ratio of F to E is equals to its charge. Therefore, the ratio of F to E should be 2 nanocoulomb. Across A to D, which one gives you this required ratio? Only A. 4 times 10 to the power of negative 9 divided by 2 is 2 times 10 to the power of negative 9, which is the required ratio, 2 nanocoulomb. Question 16. You are given with a circuit as shown below. S and T, they are in parallel, and also they're in parallel with the power supply. So everything you see over here, they are under the connection of parallel. We can conclude they have the same potential difference. According to the graph above, at what value could be the common potential difference? 4. It must be 4 volts here, 4 volts here, and therefore 4 volts at the top. The answer is A. Question 17. You have a real cell, which means there is internal resistance connected in the circuits. We have EMF, internal resistance, and the load resistance. We are trying to measure its terminal PD by connecting a voltmeter across the real cell. The reading is the EMF minus the lost volts. The lost volt is the product of currents times the internal resistance. In order to make the reading similar to the EMF, you must have the lost volt as small as possible. So you are trying to reduce the IR, make it very small. To do so, A is a possible solution. A suggests that the internal resistance is much smaller than the load resistance, which is therefore making the IR very small, and the target is achieved. Question 18. There is a current carrying solenoid. Because of this solenoid is carrying a current, there is a magnetic field created by it. The magnetic field is passing through the solenoid, creating a uniform magnetic field lines. The electron is moving towards these uniform magnetic field lines. What is the force experienced by an electron? Because of right now the velocity of the electron and the magnetic field direction, they are in parallel. Therefore, according to the equation F equals to BQV sine theta, it is right now sine 0 degree. What is sine 0 degree? The force will be 0. If there is no force acting on the electron should move in a constant velocity, undeflected. Question 19. You have a rotating platform. This platform is rotating with a kid standing on it. The kid is also performing a circular motion, and therefore there must be a force acting towards the center of circle. It is known as the requirement of centripetal force. What force could be providing such required centripetal force? Not the gravitational force, because it's pointing downward. Not the tension of the muscles, because the tension of the muscles really depends on which muscles is it being contracted. It could be going in all different directions. The normal reaction on the kid is going upward. It's still not going to the center. The answer is friction. Friction is pointing towards the center of circle, and it is helping the kid maintaining its circular motion. Question 20. There are 3 energy levels. In order to release a photon, a de-excitation is required. There are 3 possible de-excitation. The first one is the smallest jump, 6.63 times 10 to the power of negative 19 joules. The other one is the medium jump, 13.3 times 10 to the power of negative 19 joules. And the last one is the biggest leap. It is 19.93 times 10 to the power of negative 19 joules. According to the equation of energy of photon equals to HF, E is proportional to F. With a greater energy difference, there is a higher frequency. Our target is to get the two smallest frequency, which means the biggest leap is out of our consideration. The small jumps, they are the energy transition responsible for creating the smallest frequency photon. E equals to HF, which gives you the calculation of frequency being E over H. E is the energy you can choose from above. H is the Planck constant, 6.63 times 10 to the power of negative 34. Therefore, the two smallest frequency being possible is option C. Question 21. The unified atomic mass unit in gram is 1.661 times 10 to the power of negative 24 gram. The Avogadro constant, it is 6.02 times 10 to the power of 23 per mole. The answer is B. If you multiply these two numbers, it should be 1. Question 22. We are going to account for the difference between the sum of proton and electron and the single mass of an hydrogen atom. The reason behind is very likely because of the electromagnetic force. Let's go through B, C, and D why they are wrong. Strong nuclear force is not present in the proton and electron because they are too far apart. Their separation is greater than 3 femtometer. Weak nuclear interaction is wrong either, because the weak nuclear interaction is supposed to be popping up when there is an interaction. It's not staying for very long, so it's not C, as the hydrogen atom is stable for a very long duration. D, the gravitational interaction is still not a possible reason because it's way too weak in order to account for such big difference in their mass. The answer is A. 23. We are going to study a Feynman diagram of annihilation. The annihilation is electron and its antiparticle, which means a positron. These two particles, they are the starting particles of this interaction. Therefore, on the left-hand side of the timeline, there should be two particles, electron and anti-electron. Because anti-electron is an antiparticle, therefore its arrow should be going against the timeline. The answer is A. We have electron here going along the timeline to the right, and we have anti-electron pointing to the left. This arrow does not imply the anti-electron is going in time travel. It simply tells you that this arrow is representing an antiparticle. 24. We are going to burn two different fuels. We burn gasoline. Also, we burn a chunk of coal. The energy released in burning these two fuels, they are higher for the gasoline but lower for the coal. The volume of them is 1 liter and unknown for coal. The mass for coal is definitely 1 kg. How about the mass of gasoline? According to these hints, we can tell it's also 1 kg per liter. Therefore, the mass of the gasoline being burned is less than 1 kg. Let's take a look at the energy released in coal. We burned 1 kg, but there are less energy. We burn less than 1 kg of gasoline, but there are even more energy. Therefore, the energy is very compact, concentrated in the gasoline. The answer is B. The specific energy is very high for gasoline. Specific energy is defined as the energy stored per unit mass. Question 25. We have a wind turbine here. The power of a wind turbine is half a rho v cube. If you rewrite it as pi r square, it will be pi r square and then rho v cube. No matter which equation you pick, the most critical factor is the v cube. Therefore, the answer is D. 26. We are studying a simple pendulum at small amplitude. In other words, you are studying an SHM. The acceleration is proportional but opposite to its displacement. The answer is D. 27. We are studying the diffraction pattern on a single slit. Equation theta equals to lambda over b is used in this case. B is the width of slit, lambda is of course the wavelength of the slit. It is the required ratio of this question. In other words, the question is looking for angle theta. This is angle to the first minimum of your diffraction. The first minimum located at this point. It is 1 times 10 to the power of negative 2 radian. The answer is A. 28. You are trying to resolve two extremely similar lights using a diffraction grating. The equation of resolvence, lambda, delta lambda, m times n is used. Note that the lambda at the top, it should be the mean value. However, for the sake of multiple choice, we are going to do it non-cal. You can make approximation. You can make 600 at the top and 1.5 at the bottom, equals to the second order times n. Rearranging and you will get m being 200. The answer is C. 29. This is a Doppler effect question. Doppler effect suggests that when there is a relative movement between the source and the observer of the wave, there will be a change in the apparent frequency, also known as the observed frequency or the measured frequency. Here, it is an approaching motion, which means the apparent frequency should be greater than the original emitted frequency. Also, if there is a faster relative motion between the source and the observer, there will be a greater difference between the apparent frequency and the original emitted frequency. And this is a decelerating motion. Therefore, the initial speed should be very fast and the final speed would be slow. The initial difference would be great. Later on, it will be getting narrower until the measured frequency is the same as the horn's frequency, which is happening when it is stationary. The answer is D. Question 30. We have a negative particle starting at X and then it's moving to Y. This is a uniform electrostatic field, which means the magnitude of field strength is always the same and the direction is all pointing in the same direction. That's why it's uniformly accelerated. The direction of electric field is pointing from the more positive to the less positive direction. In other words, the electric field is going upward. Next, the work done by the field on the particle. This particle is a negative charge. It's moving towards the more positive terminal. Therefore, it's getting faster and faster. It's definitely gaining energy. The energy it gained would be the work done equals to the charge times the change in potential. So the work done is the product of its charge and the potential difference, 400,000 volts. The answer is D. 31. The unit of gravitational potential. You may use the equation of gravitational potential gradients. Therefore, G equals to negative delta Vg over delta R. G is the field strength here. Let's make delta Vg be the subject. It is the product of negative G and delta R. The unit of negative G is meter per second square. The unit of delta R is meter. Therefore, the combined unit is meter square as negative 2. The answer is A. Question 32. You have a planet with radius r. If you throw an object at its surface, the escape velocity is v. And if you are going to make an object staying in its orbit, Then the orbital velocity is 0.5 v. Let's calculate what is the required distance from the surface to the designated orbits. We can do so by creating a ratio of orbital speed to the escape speed. The orbital speed, according to the formula sheet, it is gm/r square root. The r here is the orbital radius. And the escape velocity is 2gm/r square root. The r in this case is the radius of the planet. After rearranging, you will show the orbital velocity and the escape speed, they are in the ratio of big R over 2 small r square roots. And according to the given information, the orbital speed is 0.5 v, meanwhile the escape speed is v. So that you can have r to 2r being 1 over 4, and r is therefore 2r. The orbital radius is 2r. With the radius being r, therefore the distance between the orbit and the surface of the planet is 1r. The answer is B. Question 33. It's a pretty complicated, tricky question. Let's begin with a drawing to emphasize every detail of the question. It begins with time equals to 0 seconds. There was a uniform magnetic field pointing to a certain direction, and there is a conducting ring going through it. When time equals to 4 seconds, the direction of the magnetic field is reversed, and the ring is still present. At the midpoint, therefore, time equals to 2 seconds. There should be no magnetic field as it is in the midpoint of reversing its magnetic field, but the ring is still present. So you can calculate the induced EMF using the 0 second up to 2 seconds, and we're going to make it in green. The induced EMF calculation is going as the Faraday's law. Let's take a look at its magnitude only. Change in its flux linkage divided by its time taken, which means we should take its final flux linkage minus the initial flux linkage divided by its time. The final magnetic flux linkage is 0 because at time equals to 2 seconds, there is no magnetic field. Initially, the magnetic flux linkage should be the product of N, B, and A. B is the magnetic field strength, A is the area, divided by its time taken. The N is the number of turns. As it is a ring, the number of turns is simply 1. So we can take 1 multiply the magnetic field strength, which is 5 times 10 to the power of negative 3, and then the cross-sectional area, A, 2 times 10 to the power of negative 4. Divided by its time taken, it took 2 seconds for the green process. In the end, it should show the induced EMF average value is 0.50 times 10 to the power of negative 6 volts. Then the answer should be D. But this question should be viewed as a whole process as well. Therefore, it could be the blue process from time equals to 0 up to time equals to 4 seconds. The calculation is just like above, but we can start with this expression, final minus initial. Note that now the final position is 4 seconds. Therefore, we can do NBA minus NBA divided by time taken. None of it is 0 in its magnetic flux linkage. But there is a but. The position of 0 second and 4 second, they are exactly reversed, which means one of the NBA should be negative. Let's take the later one be negative. So that now the calculation is 2 times the NBA divided by the new time taken. What is the new time taken? It is 4 seconds. So we have 2 times the NBA divided by 4, which means we should get back to 0.50 times 10 to the power of negative 6 volts. Still, you should get D being the answer. Question 34, the conservation law and Lenz's law. It is not the conservation of charge. Where do we see the conservation of charge? When the charges, they are redistributed at a junction, which is the Kirchhoff's law. You can find it in your formula sheet 5.2. Conservation of the energy is the answer here, simply because there is no conservation of magnetic field and conservation of masses. The conservation of energy applies here because the kinetic energy of the moving ring or the moving coil is reduced at the expense of you have an induced EMF, which gives you a certain current. You convert the kinetic energy of the ring into electrical energy as the current passes through your ring. Question 35. You have a resistor with these labeled value connected to an alternating current circuit, and there is a peak voltage of 10 volts. Peak voltage of 10 volts. And we are looking at the average power dissipation. The average power dissipation can be calculated as V squared over R. Of course, you should get the RMS value if you are after the average power dissipation. The RMS value is the peak value divided by root 2. You can substitute every number in. You have the peak voltage squared divided by R at the same moment times 1 over 2. It is half times 10 squared over 2. The answer is 25 watts. A. Question 36. You have a capacitor about to discharge. The equation for discharge in a variation with time is Q equals to Q0 e to the power of negative t over tau. According to the definition of capacitance as charge divided by potential difference, you can have the initial charge as the initial capacitance times its initial potential difference, followed by the e to the power of t over tau. Tau is the time constant of the system. Its numerical value is calculated as the resistance times its capacitance, so you can put R times C here. Lastly, we substitute the numbers and the symbols given by the question. We have capacitance defined as X, so we have Q equals to XV times e to the power of t over Rx. The answer is D. Question 37. The answer is C. And actually, you can simply memorize this conclusion, but I will still show you the full derivation here, even though the following derivation might be slightly beyond the syllabus. Let's take a look at the uncertainty principle. Uncertainty in its position, uncertainty in its momentum, their product should be greater than Planck constant over 4 pi. And if there is an electron inside a nucleus, then the diameter of the nucleus could be the uncertainty of the position of the electron inside. The diameter of any nucleus should be roughly in the order of magnitude 10 to the power of negative 15 meter. It is just like the Fermi radius in your formula sheets. Next, we can have 10 to the power of negative 15 times its momentum greater than h over 4 pi. Momentum is h over 4 pi times 10 to the power of negative 15. Also, the momentum of the electron is the product of its mass and its velocity. So, you have h over 4 pi times 10 to the power of negative 15. Lastly, you have v being the subject. then you will show h over 4 pi times 10 to the power of negative 15 times the mass of electron. Put everything into your calculator and you will find that the speed of electron will be greater than the speed of light in vacuum, which is not possible for our current understanding. So the answer is C. The electron simply can never exist in a nucleus because to do so, it would require a speed greater than the speed of light in vacuum. Question 38. It's about photoelectric effects. And there is an external variable power supply provided to the photocell. What do the x-axis mean? The x-axis is the applied voltage. If you are on the negative applied voltage, which means the plate on the right-hand side here is negative. And such negative plates would repel any incoming electron. Let's take a look at X. At this point, you can see the currents reduced to zero, which means if you successfully provide the required potential difference, the electron will no longer reach the negative terminal so that there is no electron flow anymore. Such potential difference able to stop the current flow is known as the stopping potential difference. When do we require a high amount of stopping potential? When the electron they are moving very fast. If the electron is moving at a high speed with high kinetic energy, the negative terminal should be very negative so as to repel the high speed incoming electron. In opposite, if the electron is moving slowly, then the negative terminal can be slightly negative. Still, it could be able to repel any incoming electron. By having this idea in your mind, you can check X is stopping potential is more negative than Y and Z. So the speed of electron for X is faster than the speed of electron in Y and Z. When do we obtain some higher speed of electron? We can obtain higher speed of electron by having a higher frequency of light. This is the equation E max equals to HF minus work function. To result in a higher kinetic energy of electron, there should be a higher frequency of light. Therefore, we can conclude statement 1 is wrong because the electron from X is faster. Therefore, the frequency of light of X is faster. The frequency of light in X is higher. Similarly, by checking the stopping potential value of Y and Z, they're the same point. You can tell the electrons of Y and Z, they are moving at the same KE, and they require the same stopping potential difference. Originally, they were given with the same frequency of light. Y and Z, they are the same frequency of light. How about the intensity? You can study the intensity by studying zero applied voltage. Therefore, these points, the y-intercepts. Y and Z, they were the same frequency of light. So what's varying their current? If the electron, they are moving at the same speed, why the photocurrent of Y is still higher than that of X? Because in situation Y, the electrons, they are moving slowly. And so as Z. Z is also moving slowly. But the population of Z is lower. There are less electrons moving slowly compared to that of Y. There are lots of electrons moving slowly. Still, you have a greater current of Y than that of Z. So the intensity of Y should be higher. With greater intensity of light, there will be more photon falling onto the metal plate and more photoelectron being released. The answer is C. Let's take a look at these two simulators. This is a simulation of light source from the left pointing to the right hand side a metal surface, and photon moving from the left to the right as a result of electron being released from the right hand side back to the left hand side. Both light sources, they are under the same wavelength of 500 nanometer. Therefore, the two photons in two simulators, they have the same frequency and the same energy. As a result, you can see that the electron, they are released at the same speed and same kinetic energy. That's why, back to the question, Y and Z, they have the same required stopping potential difference. However, their intensities are different. The one on the right is obviously brighter, more photons are released per second, and therefore more electrons are released per second. You can see that in both simulators, they took about 1 minute. But the one on the left received only 30-ish electrons, but on the right there is 140 electrons. Definitely is a result of the number of photons per unit time and the number of electrons per unit time. The link to the simulator is in the description box. You can give it a try on your own. Question 39. It is the radiation released by an unknown sample. There is activity and the number of remaining nuclei graphs provided. You can check the equation A equals to lambda m. Note that this equation is not provided in your formula sheets. You can either memorize it or use the following hints to derive these two equations. There are two equations provided by the formula sheets, starting with n equals to n0 e to the power of negative lambda t, and a equals to lambda n0 e to the power of negative lambda t. By the symmetry, you can tell actually this part should be equals to a0. So that you can have a0 equals to lambda n0. That's how you derive the required equation here. However, I do recommend you simply memorize the equation. It's a very simple three symbols equation. And how do we use it? You can check the y-intercept. This point being the a0, this point being the n0. So you have a0 equals to lambda n0. A is 0.7 times 10 to the power of 6, unknown lambda. N is 1 times 10 to the power of 6, then you can get lambda is 0.7. And what unit do we give is depends on the x-axis unit. We have second -1. The answer is A. The final question, 40, it's about the existence of neutrino. The answer to this one is D. And the explanation is not beyond the syllabus. I do recommend you to understand and fully memorize the reasoning below, because I have seen some long questions related to the following calculation as well. It's all about the nuclear energy levels. The nuclear energy level, they are discrete. So it could be from one energy state to another energy state. And such energy conversion is done by releasing a beta decay. For instance, it was as 10 joules, and then it's going to 8 joules. Then the difference, therefore 2 joules, is carried by the emitted particle. If there is only beta particles being released, then no matter is it the first measurement or the second measurement or the third measurement, you will always get 2 joules, because the energy difference is 10 reduced to 8 is always 2 joules. But the actual measurement, they were sometimes being 0.2 joules, sometimes is 0.7 joules, you may get 1.6 joules, 1.9 joules, stuff like this. Why a range of different possible numbers is given out even though the energy difference is always 2 joules? The only possible explanation is there is another particle, invisible, so that we cannot detect it. That is the neutrino, or maybe antineutrino. This particle is carrying the missing amount of energy. Therefore, if the beta is 0.2 joules, then at that moment, the neutrino is 1.8, so that they add up to be 2. If the beta particle is 0.7, then the neutrino is 1.3. In 1.6, that would be 0.4, 0.1. So that it's always adding up to 2 joules. The answer is D, because the beta itself, it gives you a continuous spectrum. This is the continuous spectrum. In order to obtain a beta continuous spectrum, there must be an invisible partner accounting for the missing amount of energy. That is the neutrino. This is the end of my complete solution, and I will see you guys next time.